Hello everyone, today we'll talk about the problem lucky numbers in a matrix. We're given a rectangular matrix consisting of distinct integers, and we have to return all numbers, all lucky numbers, where a lucky number is defined as a number that's both the minimum element in its row and the maximum element in its column. So in one direction we care about it being a maximum, in the second direction about it being a minimum. We have to return all of those elements. Of course, the simplest idea would be to just go through all the elements and for each element naively check if it's lucky, right? So in essence we have m times n different elements that we have to check, and in general we'll have to check all the elements, we'll have to look at every element, so O of m times n is the minimum complexity, and also for every check we can do it in m plus n time by looking at both its column and its row. So that is a brute force. And how can we make this solution faster? Well, of course, that check if the element is minimum or maximum in its row or column can be performed quickly by pre-computing the maximums or appropriately minimums of every row and column, because they don't change along the time that we run our algorithm. And then the check can be, we know row and column, we see the value at that row and column, we see if it is a maximum and minimum appropriately, and we return the result. And that will already give us m times n, and it's impossible to do anything better. But of course we can do it explicitly, go through all the candidates, check appropriate minimum, maximum, and add it to the list if it's a lucky number. But we can also, for instance, check the set of all the minima on rows, all the maxima on columns, and the result will just be the intersection of those two sets, because our numbers are distinct. So if a number appears both as a minimum in some row and as a maximum in some column, then it has to be the same number because all the numbers are distinct, so we know that it indeed is a result. So that is a shorter way to write it. And of course, getting a minimum over rows is very easy, because we just have to take simply of the minimum of every row of the matrix, so map the minimum function over the matrix. To do it over columns, we either have to transpose the matrix or do something more complicated, because we are going against the grain, as it were. And we could of course stop there with either of the optimal solutions, but there is also a pretty funny idea here, because this will of course work even if we change the definition of lucky numbers to be, for instance, maximum in both column and row, or minimum in both column and row. However, in this specific instance, how many lucky numbers can there be? Because we know that we can look at all the row minima, we can look at all the column maxima, and take the intersection of those. And is it possible that that intersection consists of more than a single number? Because of course it can consist of a single number, but, or maybe that even isn't clear, but it's easy to see by examples that it's possible to have a lucky number in a matrix, and indeed we're going to have that number. But is it possible to have more than one? And when you work out through some examples that it's not possible to have more than one lucky number, then the natural question would be how to prove it. And of course, if we have two possible numbers that somebody tells us they are both lucky in our matrix, they have to be in different rows, different columns. That's obvious from the very definition. And so if we have here a number A and here a number B, which are both lucky, then when we look at their columns and rows, right, there are two positions that are common. So let's say a position P and Q in this square, because P is in the same row as A, the same column as B, likewise for Q. And we know that for A to be a lucky number, it has to be minimum in its row. So A has to be smaller than P. In particular, because it has to be smaller than everything in its row, that's not it. And it has to be greater than Q because it has to be a maximum in its column. Great. And B has to be greater than P But also, since it's on the same row as q, it has to be smaller than q. And a simple exercise for you is to find two integers, a, b, that for those two given integers, all of that is both true. So yeah, we see that there is only one number, because if we have two numbers, then we see that it's impossible, because the inequalities here are in different directions. So either the interval from q to p or from p to q is an interval that actually has any numbers in it.